Welcome to Organic Chemistry. In this video, we will focus on aromaticity, as well as the Diels-Alder cycloaddition reactions and electrocyclic reactions. Let's get started. Before we can talk about aromaticity, or reactions like Diels-Alder and electrocyclic reactions, we need to return to something much more fundamental. Every atomic orbital, every molecular orbital that you have ever seen is a wave function. Not a picture, not a location, but a mathematical solution. Specifically, every wave function that you've encountered, whether atomic orbitals or molecular orbitals, is specifically an eigenfunction of the Hamiltonian operator. When we write that the Hamiltonian operator acts on a wave function and provides us with the eigenvalue of times that wave function, we are saying something very precise. We're saying that only certain shapes or states are allowed, and that each allowed shape state has a fixed energy. Those shapes are atomic orbitals or molecular orbitals. Those energies are their eigenvalues. An eigenfunction is not static. It is a steady state pattern. When the Hamiltonian acts on it, the function does not change shape. It only scales. That's the defining feature of the allowed state, of that eigenfunction. So crucially, standing waves that are wave functions, or specifically eigenfunctions, require such boundary conditions and are associated with specific energies that we call its eigenvalue. Now, in a linear conjugated system, the p orbitals overlap along a chain, and the ends most definitely matter. The ends force nodes. They enforce standing wave behavior. This is why linear conjugated systems form a ladder of molecular orbitals with increasing number of nodes. The more nodes, the higher in energy. So far, nothing mysterious. When p orbitals conjugate, electrons are delocalized. Their energies split, and new symmetry emerges. This is why conjugated systems can give multiple products, such as 1,2 or 1,4 addition. But at this stage, the system is still open. There is no requirement that the wave function reconnect to itself. But now we do something radical. We now close the conjugated chain into a loop. And the moment we do that, the physics changes. Because now the wave function must satisfy these conditions that the wave function as a function of theta plus 2 pi is equal to the wave function as a function of theta. This is not a chemistry rule. This is a boundary condition on a wave. So aromaticity is equivalent to conjugation with periodicity. Aromaticity is not some quote-unquote extra stability. Aromaticity is a conjugated pi system whose wave function is periodic and self-consistent. Once you impose periodicity, only certain phase progressions are allowed. And those phase progressions determine which orbitals are occupied, which orbitals are degenerate, which are stable, and which are unstable. In the case of the three-membered ring, cyclopropanol systems with 3 p orbitals, the phase can only advance in steps of 120 degrees. That gives us one fully bonding molecular orbital and one degenerate anti-bonding pair. If the bonding molecular orbital is completely filled, the system preserves symmetry. That's aromaticity. If it is half filled, symmetry breaks. That is anti-aromaticity. Degenerate orbitals mean different eigenfunctions with the same energy. Literally, D is from and gen life, so of the same generation, of the same life. This is not accidental. Degeneracy appears because the wave function can propagate clockwise or counterclockwise with the same energetic cost. When those degenerate orbitals are fully filled, their phase distortions cancel. When they are only partially filled, they reinforce instability. For a four-membered ring, the phase advances in 90-degree steps. This creates degenerate non-bonding orbitals at the Fermi level. If electrons are forced to occupy these half-filled states, nodes cannot be eliminated, and phase strain is unavoidable. That's anti-aromaticity. Not because quote-unquote 4 is bad, but because the wave function cannot resolve its boundary conditions. In five-membered rings, a heteroatom can donate only one lone pair into the pi system. Remember, if it does this, it's conjugated, and so therefore that heteroatom would be sp2 hybridized. It cannot donate two pairs into the ring system. That lone pair completes the filling of the degenerate bonding set. And once again, complete filling preserves symmetry and therefore yields aromaticity. This is why pyrrole, furan, and thiophene are aromatic, and why the second lone pair does not participate. With 6p orbitals, the phase advances by 60 degrees. Two degenerate bonding orbitals exist, and both are fully filled. Benzene here is the ideal case, and this is the most stable topology. There is no phase strain, and there are no partially occupied degenerate orbitals. Benzene is not special because it's common. It is common because it is topologically optimal. All this leads to Hückel's rule, which now makes sense. This is a common rule that says that aromaticity will follow 4n plus 2 pi electrons. This is not numerology. It is simply the number of electrons required to completely fill all bonding and degenerate bonding eigenfunctions under periodic boundary conditions. That's it. Nothing mystical. Why does this matter for reactions? Here's the pivot. If orbital symmetry and phase continuity determine stability, then changing orbital occupancy must change the allowed reactions. And that's what we'll see happen in electrocyclic reactions, cycloaddition, which we will focus on in Diels Alder reactions, as well as additional reactions called sigmatropic rearrangements. It's important to note that thermal reactions preserve Hückel topology. Under thermal conditions, reactions occur on the ground state potential energy surface. That means orbital occupancy will not change. Degeneracies stay where they are, and the system remains Hückel-like. This is why thermal pericyclic reactions obey Hückel selection rules. The topology is preserved. But this cannot explain everything. There are reactions that are forbidden thermally, but allowed photochemically. And Hückel theory alone cannot explain that. For photochemical excitation reactions, when light is absorbed, an electron is promoted from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And that is not a small change. It reorders the orbital occupancy. And when the orbital occupancy changes, the effective topology of the pi system changes. This yields the Möbius model. In a Möbius system, the boundary condition becomes the wave function as a function of theta plus 2 pi is equal to negative of the wave function as a function of theta. The wave function must change sign after one full loop. And that single minus sign changes everything. That boundary condition introduces an unavoidable phase inversion and eliminates degeneracy in the lowest bonding orbitals. So in the excited state, this redistribution actually lowers the total energy. And so electron counting flips. Under Möbius topology, 4n pi electrons will be aromatic. So in this first part of the video, we focused on aromaticity as really a boundary condition for wave functions. Now we're going to use that same logic to understand pericyclic reactions. We begin with substituent effects, inductive versus resonance effects. There are two distinct ways substituents can influence pi systems, either through inductive effects, which act through sigma bonds, or resonance effects, which act through pi conjugation. We must consider these both together. Induction redistributes electron density, resonance redistributes wave function amplitude. In electron donating groups, they raise the energy of the pi highest occupied molecular orbital and increase electron density in the conjugated system. This makes the molecule a better electron donor. With electron withdrawing groups, they lower the energy of the pi lowest unoccupied molecular orbital and stabilize developing negative charge. This makes the molecule a better electron acceptor. Reactivity is therefore controlled by how close the donor and acceptor orbitals are in energy. The Diels-Alder reaction is a 4 pi plus 2 pi cycloaddition reaction. It is concerted, stereospecific, thermally allowed. Both components react on the same face, suprafacially. Only the S, referring to sigma, cis conformation is allowed. This provides continuous orbital overlap and proper phase alignment. The S sigma transconformation cannot react, not because of energy alone, but because the orbital symmetry simply cannot connect. Now we also look at the endo versus exo question. Electron withdrawing groups on the dienophile stabilize the transition state, and they do this through secondary orbital interactions. This is not sterics. This is orbital overlap in the transition state. Regioselectivity emerges when electron donating groups raise the diene's highest occupied molecular orbital. And when electron withdrawing groups lower the dienophile's lowest unoccupied molecular orbital. The largest HOMO coefficient aligns with the largest LUMO coefficient. Orbitals react where their amplitudes match best. And that's it. Bond formation requires symmetry-allowed overlap of interacting molecular orbitals. The smaller the energy gap between the dienes HOMO and the dienophiles LUMO, the lower the activation energy. This is why electron donating groups and electron withdrawing groups accelerate the reaction. Energy matching controls rate. Symmetry controls permission, and both are required. If we compare 4 pi plus 2 pi cycloadditions, we see they are allowed thermally, but 2 pi plus 2 pi cycloadditions are forbidden thermally. Why? Because 2 pi plus 2 pi cycloaddition would require a Möbius topology in the ground state, and that topology is not accessible thermally. Although we will be obsessed with thermal reactions in this unit, photochemical reactions are a domain of expanding research, active research. And so I don't want you to get the takeaway that Möbius topologies are just nonsense or something just not allowed. The Woodward Hoffmann cycloadditions table shows us that thermal reactions preserve Hückel topology versus photochemical reactions access Möbius topology. Light changes literally the orbital occupancy, and occupancy changes topology. With electrocyclic reactions, we can simplify even further. We only need to examine the symmetry of the highest occupied molecular orbital. That orbital will determine how the terminal p orbitals must rotate. For thermal electrocyclic reactions, 4n pi electrons must conform conrotary versus 4n plus 2 pi electrons must conform disrotary. This preserves Hückel aromaticity in the transition state. Of course, if light were to excite an electron, the HOMO symmetry would flip and the allowed rotation would reverse. So only under those conditions would 4n pi electrons would conform disrotary and 4n plus 2 pi electrons would conform conrotary. Same molecule, same electrons, different orbital occupancy. And that covers our video on aromaticity and pericyclic reactions. Electron count determines allowed topology. Topology determines allowed motion and reactivity. Till next time, Crip.